Edexcel Core Pure, second order differential equations 3, modelling with second order differential equations. 3.2 damped oscillations. So we've previously seen how simple harmonic motion can be modelled by this really important second order linear homogeneous equation, d2x by dt squared equals minus omega squared x, and we usually give the general solution in the form where the constant amplitude is a and the period for one complete oscillation of the motion is given by 2 pi over omega, and if there is a phase shift then the phase shift would be epsilon over omega to the left if epsilon was positive. So although this is a good model for some simple oscillating systems, there are many situations where the amplitude of the oscillation will decrease over time, and this is called damped oscillations. So for example, if you did have a mass bouncing up and down on the end of a spring, then eventually over time, due to air resistance, those amplitudes would decrease, although the oscillations would maintain the same time period, the amplitudes would decrease. So now we're going to look at damped oscillation systems in a bit more detail, and a typical differential equation would be d2x by dt squared plus 2 dx by dt plus 10x equals 0. So this part and this part, the beginning and the end, that's the simple harmonic motion, but we now have this extra term that is the damping effect. So we're now adding a resistive element to the differential equation, where the resistance is proportional to the velocity. So now if we look at the auxiliary equation, we get lambda squared plus 2 lambda plus 10 equals 0, and we could complete the square here, or we could use a quadratic formula, but we get lambda is minus 1 plus or minus 3i, and that will have the general solution x equals e to the minus t p cos 3t plus q sine 3t. So the 3, the imaginary part 3, we can see there, and the minus 1 is there in that index, x equals e to the minus 1t. So that's our general solution for this damped oscillating equation. So again, this is the term here that is creating the damping effect, and we end up with a complex solution for lambda, and therefore we end up with a general equation here, and it's this e to the minus t term that's creating the damping effect. So now we have some conditions. We are told that when t is 0, x is 0, and when t is 0, the velocity is 1. dx by dt would be the velocity. So we're going to use these now on our general solution to find a particular solution. So for example, when t is 0, x is 0, so that's given. Therefore, p would be 0. So we now have an improved solution of x equals e to the minus t q sine. And we now need a dx by dt. We need to differentiate this to get a velocity expression. So using a product rule, that's minus q e to the minus t sine 3t plus 3q e to the minus t cos 3t. And we know that when t is 0, dx by dt is 1. So that would give us 1 on the left hand side and 3q here on the right hand side. So we now have a value of q, which is a third, and therefore we have the particular solution, the ps, which would be x equals a third e to the minus t sine 3t. So this motion we started the motion at the origin with a velocity of 1, and that gives us this particular solution. So we can see it's an oscillating solution due to the sine 3t, but the damping effect is given by this e to the minus t term. So we used this condition to substitute in order to find the value of p, and we substituted this condition in to find the value of q to give us our particular solution. So now we can see the solution on this curve. This is our time axis, this is our displacement x, and we can see that when t is 0, x is indeed 0, and the gradient or the velocity when t is 0 would be 1. And we can see that this oscillating system of sine 3t is indeed decaying due to the e to the minus t term. So we can see the amplitude is reducing all the time as t increases. So we can see that the solution does show an oscillating system of an SHM form, but the amplitude is now decaying, and the amplitude will lie between the curves x equals plus or minus a third e to the minus t. So that's the effect of the damping on the oscillating system. In the next video we're going to be looking at damped oscillations and plotting and interpreting solutions.